Okay. Hello everyone. So we're going to continue with questions on cache memory. So this is the first question we're doing, and this is from test 1 2022, and it is: consider a machine with byte addressable memory of 64 kilobytes and block size of 8 bytes. Assume the directly mapped cache of 26 bytes is used with this machine. So how is the main address divided into tag, line, and word values? Then if the same cache is organized as a two-way set associative cache, that uses least recently used replacement algorithm, right? Then how is the main address divided into tag, set, and word values? And when a program is executed, the processor reads the data sequentially and the following addresses. So we have access number 1, 2, 3, 4, 5, 6. These are decimal values. So I didn't copy the full question here, but we're supposed to show whether the address is a hit or a miss here. Yeah, I didn't copy the full question. So how do we start this? So this is my procedure, how I like moving around with this question. So first thing is we're going to say our main memory, right? We're just going to say our data. So first thing is our main memory. Our main memory. So our main memory is 64 kilobytes. Right? 64 kilobytes. Now, what is 64 kilobytes? Well, first of all, is we just need to understand how memory works. So, firstly, we have our bytes quite right here. So we can say 2 to the power 4. This is going to be 4 bytes. Or this is going to be 16 bytes, right? 16 bytes. Then now, as we continue going, so in powers of 10, in short. So if we have 2 to the power 10, so we're going to select 2 to the power x, right? Then 2 to the power 10x, 2 to the power 20x, and then 2 to the power 30x, right? So basically what this means is that as long as our x is less than 10, right? As long as x is less than 10, what this is in bytes, this is in kilobytes, this is in megabytes, and this is in gigabytes, and so on and so forth, right? So this is bytes, kilobytes, whatever. So now, in doing this, in fact, it's supposed to be plus here. It's supposed to have a plus over here. So 10 plus x, 20 plus x, whatever. So gigabytes there. So just something to remember quickly as we go on to multiplying this. So first of all is, what is 64, right? So we have 2 to the power. So we know what it's in kilobytes, so it's going to be 2 to the power 10 plus. What is 64? 64 is 2 to the power 6, right? If we do the multiplication, there are 2 to the power 6 on our calculators, that's 64. So this is 2 to the power 64 like that, which then gives us 2 to the power 16 bytes. 2 to the power 16 bytes. Now, we've been told here that our memory is byte addressable, right? Is byte addressable. What does this mean? And this is going to be very useful as we continue knowing. But what byte addressable means is that each location stores 1 byte, or the size of a word. The size of a word, right? And don't confuse this with the size of a block, but size of the word is 1 byte, right? So meaning that whenever we address a word, we address 1 byte. So meaning this is the same as saying 2 to the power 16 words, right? 2 to the power 16 words. We are going to further elaborate on this as we look at the question that isn't byte addressable, but is something called word addressable, which can be confusing, but yeah, we're going to encounter that later. Then now, our address bits. Our address bits. What are our address bits? Well, we know that our main memory is 2 to the power 64 bytes, right? So meaning we need basically 16 bits, right? The power there, we need 16 bits to work with our entire memory address. So this is the size of our address. This is the size of our physical address, in short. In the previous explanation video, when I was referring to PA, basically this is what I meant, these 16 bits. Then now we have our block size. You can arrange these however you want, but this is how I prefer doing them. So we have our block size. what is our block size? Well, our block size, we've been told in the question that it is 8 bytes. What is 8 bytes? 8 bytes is 2 to the power 3. 2 to the power 3 bytes. So just convert it to a power of 2, which is then just equal to 3 bits for the word. So we have 3 bits for the word, right? So each word is separated, each word uses up 3 bits of our physical address. What next? I want to calculate cache size right now, but yeah, let me just show that there as well. So our cache size, so because we're going to come back to this anyway. Our cache size, this is equal to 256 bytes, right? Which is just 2 to the power 8, 2 to the power 8 bytes, which is equal to 8 bits. This will prove very useful as we go on. So now, we need to, first of all, the first part of the question, right? This first part of the question says, how is memory divided into tags, what is that question? Into tag, line, and word value. So right now, all we have is the bits for the word, right? All we have is the bits for the word. But if you remember when we were doing that discussion, right? What we said is that if our physical address is separated like this, if this is our physical address, right? If this is our physical address, what we know is that if we have our words here and then this is our line, right? Our line, word, and then our tag, we know to say this one over here represents our cache size. This one over here represents the number of blocks, right? So we have that there and that there, right? How will this work out for us? Well, basically we can say our line bits, this is just equal to our cache bits, right? The number of bits taken up by the size of our cache, which is this right here, minus our word bits. What are our word bits? What are our cache bits? Our cache bits are 8. Minus, what are our word bits? The size of our words takes up 3 bits there, which then just gives us 5 bits, right? And then what is our tag? Well, since we have the line and then the word, mean our tag itself is just equal to the physical address, which is 16, minus 5 minus 3, which is just 16 minus 8, which is just equal to 8, right? So meaning, what we can then surmise, right? What we can then conclude is that our address is split into the following. We have 8 bits for the tag, 5 bits for the line, 3 bits for the word, right? We have that there, and then we're going to have, this is tag, line, word, right? Of course, so this is how the things are demarcated, and then how you would do this is just draw this thing here. So 8 bits, 5 bits, 3 bits. So this is the first part of the question, right? So this is the first part of our question. Now let's look at the second part of our question, right? Second part is, if the cache is then organized into two-way set associative cache, right? That uses least recently used replacement algorithm. Again, we'll talk about, I said we'll find the replacement algorithms as well go in, which is this one here. And then, how is the main memory divided into tag, set, address values, right? So this one, the first one, direct mapping, it had the line, but set associative had the sets there. So now, if we look at B1, right? So what we've been told first of all in the question is that we have two-way. So our k-way set associative map is 2, right? So our k is equal to 2, right? How are we going to use this value? Well, first thing is that we want to find the number of sets, right? We want to find the number of sets. How do we do that? Well, we have a formula that we can use for that. So remember, we said our cache size, right? When we said our cache size, the size of our cache, right, That's our cache, right? This is equal to k times 2g plus w, right? So this is k times 2 to the power g times that there, right? So how do we do this? Well, what is our cache size? We know that our cache size is 256 bytes, which is 2 to the power 8. Right? This is then, what is our k? Our k is 2 times 2. We want to find the number of sets that we have. So just a correction of what I said in the previous video. I said we're given the number of sets. We're actually given k sets we have to find for ourselves usually. Then plus, what is our word size? Our word size stays constant in this case because the size of each line in our cache. So basically what we're going to have here is still those 3 bytes. Then we're going to do our calculations. So we're going to say, okay, 2 to the power 8 is equal to 2 to the power g plus 3, right? Plus 3 plus 1, because this is 2 to the power 1. Then we just take our powers here. We say, okay, 8 is equal to g plus 3 plus 1, which means g is just equal to 8 minus 4, which is equal to 4, right? 4 bits. So basically our address now is split as follows. Our address will just be split in this way. We're going to have this guy over here. We're going to have this guy over here, which is then going to be, we maintain those 3 bits. Here we have 4. Then for our tag bits are just going to be 16 minus 7. So 16 minus 7, which is just the remaining number of bits. So we have 9 there. Right? We have 9 there. And something that I noticed, I could be wrong here, but what I noticed is that basically the number of if you have your line size, right? If you have your line size, basically we're doing, just like I tried to do in my head. I'm not sure if I was right, but if you have your k will always be a power of 2. So you can just say, if let's say we have 8, we can say, okay, 2 to the power 3. So I mean, from my line, I'm just going to take away 3 bits and then add 3 to my tag bits, which is what we did here, because this is power 1. So we've just taken away 1 from our original 5 here, and then added it to the tag there. But anyway, I digress. Just something I wanted to say. Yeah. So anyway, let's continue with the second part of our question, which is a bit longer. Well, not exactly, but the way I liked doing it was a bit long. But yeah, I just like staying organized when I was doing this. But so what we're going to do is, first of all, I'm going to discuss the algorithm that we have here, right, before we move on to actually solving the question. So we say this is our we say this is our cache size, right? So we have our cache size here. Well, we have this is our main memory, and then we have our cache. Now when we load our cache with whichever blocks that we're going to load it with, when we load it with whichever blocks that we have here, let's say our cache is full, right? So let's say our cache here, and this is our memory. Let's say this cache is full. Then we want to get another block and put it in our cache. Now since it's full, we need to find a way to replace what's in the cache. This is where we have our replacement algorithms. The first is FIFO. What FIFO is just replace the block that has been there the longest. So say if we have, let's say, 5 lines, right? We have 5 lines, and then we've occupied all those 5 lines. Basically, for first in, first out, well, basically just going to replace the one that has been there the longest, right? So let's say this is set associative mapping, right? We're going to replace the one that has been there the longest, which would be 0. In the next, again, if we come and load another one, we'll come and replace 1, because the counter for line 0 just reset, right? Then we just do that. So we just keep track of the one that has been in our cache the longest, and it's the one we remove. The next one is least recently used, and what least recently used means is get the one that we haven't used the most recently, right? So each time we access our cache, we keep track of which one we are just from using. Then now we say, okay, out of everything that we have in our cache, which one haven't we used the most recently? If we find it, it's the one we replace. Right. So as we solve this, we're going to, of course, keep track of this stuff. So this is quite a longer part. So to avoid any disturbances, I'm going to stop this video here and then to continue in the next part.